One of the most interesting and useful patterns in all of mathematics is the numerical array called Pascal's triangle. Essentially, on the top row and the outside diagonals are just, you can just write a bunch of ones. Everything's ones. On the inside is we take any two numbers on the inside, any two numbers that are next to each other, and add them together. They'll add up to the number directly below it. So you see here that this example here, 4 plus 6 is equal to 10. So the 4 and the 6 is on above and the 10 is below. This 21 right here, 15 plus 6 is 21. That gives me that number. And that's true of every number inside here, is that you add up the two numbers above it, you get that number below. You get that number. So let's try to figure out the next row. And what we do is we assume that everything on the outside is just zeros. So the first number is going to be a 1. The last number is going to be a 1. Now, 1 plus 7 is 8. And then the next two over is 7 and 21. That's 28. And then 21 plus 35 is 56. 35 plus 35 is 70. And then 56, 28, 8. Some patterns that are that you can find in Pascal's triangle. Well, the triangular numbers show up. If you think like 1 plus 2 is 3, 1 plus 2 plus 3 is 6, 1 plus 2 plus 3 plus 4 is 10, 1 plus 2 plus 3 plus 4 plus 5 is 15. That shows up along the diagonals. You see it's shaded there. Adding the numbers along the diagonals, a different set of diagonals, gives the Fibonacci numbers. So if I take that very top, that 1 there at the top, that's 1. And then just below that is a 1. And then the 2 that are below those, below that gives me 2. 1 plus 1 is 2. And then you have 1 plus 2 is 3. 1 plus 3 plus 1 is 5. 1 plus 4 plus 3 is 8. 1 plus 5 plus 6 plus 13 is 21. It's 13, and then you get the 21 there. See, those are Fibonacci numbers. Another use is in algebra. It's a shortcut for polynomial expansions. So a bit beyond our class, but you can see that like this bottom one, the x plus 1 to the fourth, those numbers in front of the x's, the coefficients, the 1, 4, 6, 4, and the 1 at the end, those are Fibonacci numbers. I mean, those are numbers that go in the Pascal's triangle. There are also interesting patterns if we simply consider whether the terms are odd or even. So the pattern below is obtained by coloring the odd numbers in Pascal's triangle. So I shaded all the ones that were odd and left the even ones alone. And if I continue this on forever, I get the fractal called Sierpinski Triangle. So in Sierpinski Triangle, you basically start with a triangle, and then you chop out the middle, and then so it gives you 3 smaller triangles, and then each of those smaller triangles, you chop out the middle, and now you have 9 even smaller triangles, and then you chop out the middles of those. So you have 27 of them now. And you basically repeat that forever. That's called a Sierpinski triangle. And you can kind of see that by, for whatever reason, that Pascal's triangle shows you the Sierpinski triangle. And I'll leave this for you on your own. See if you can figure out any other patterns.